All right, so radicals. So free radicals, essentially what they are is that they are unpaired electrons. So if everything that you've learned up to this point, bonds, whether single, double, or triple, lone pairs exist as pairs of electrons, and they are relatively stable. Lone uh, single electrons are something we call free radicals. They are extremely reactive, and they will just keep reacting. Um, they are highly energetic, and this is what can damage your system. So if you think about things that are bad for your body, um, have you ever heard in commercials like free radical damage for like skincare stuff? Or next time you see a commercial for skincare, like or sunscreen or something like that, just listen when they say like oxidative damage or um, free radical damage or stuff like that. This is what they're talking about, because like sunlight can cause these things. Oxygen can cause these things, but the idea is that a bond is going to split like it does here. So these two electrons are going to split. One will go to one atom, one will go to the other one. And this is what's called a homolytic bond cleavage, because it's one bond splitting by itself. So now the important thing you see here is the difference in arrows. So when we do our normal mechanism arrows, like we do arrow pushing, such as removing a bond or a lone pair attacks or something like that, it's a regular arrow. When we do these mechanisms and we're talking about a radical, it's a fishhook. So it's only one side because it represents just one electron. Right? So then the idea here is that when you have this idea of a carbocation and carbanion. So carbocation, remember, is when we are missing a lone pair, we're missing electrons, right? So this is um, hypo. Oh, I forgot the term for it. It's got less than 8 electrons. Hypovalent. There you go. Oof, that was rough. So this is hypovalent, right? And this is an sp2 hybridization. But when we have a carbanion, and this is a carbon with a lone pair, this is still sp3 hybridized, right? So the difference here is that carbocations have an empty p orbital, and then the carbanion has a full p orbital. So like this is still, the hybridization is still occurring. So this is going to be important because now when we come here and we think about the radical structure of geometry, radicals appear to be trigonal planar. They appear to have this sp2 hybridized, or you can say they have shallow trigonal planar sp3. But just for the sake of argument, we just usually say that it's sp2 hybridized. All right. Melissa, how you doing?
Hi, I'm good, and you?
Good. We're just talking about radicals. We just started.
Okay.
All right. So free radical stability. Um, essentially speaking, they have no formal charge, but they're still electron deficient, and even worse than that, they're not paired. So they're very reactive, and they follow the same stability trend as carbocations. So just like carbocations, they're going to be stabilized with resonance. They'll be stabilized with tertiary carbon, secondary carbons, then primary carbons, then methyls, right? So the more carbons you have around, the more stable you are. The more resonance you have around, the more stable you are. And so free radicals and carbocations have the same stability trends. All right. So now if you look here at our free radical stability, and thankfully Professor Davis put this in a nice chart in. I like her PowerPoints. They're very nice and easy to read. Much better than mine. All right. So bond strength is inversely proportional to carbon radical stability. The more stable the resulting radicals, the weaker the bond. So if you think about this decreasing BDE, our most stable one is going to be our tertiary, then secondary, then primary, and then methyl. So essentially, the relative stability of our radical species is dependent on the original bond strength that we're breaking. Um, but again, the important thing to remember is it's just that um, the tertiary is more stable than secondary, more stable than a primary, so on and so forth. All right. So now, just like with our carbocations, we can have this stabilization by resonance, right? So when you have a double bond like this position here is called the allylic position. Have we used that term before? I don't remember. It's all starting to blend together. Well, if we haven't, this is going to be your first time you see it. So when you have a double bond, a carbon that is one carbon away from a double bond is called the allylic position, and it's very useful for a lot of stability talk. So when we think about our different types of stabilities and whatnot, this allylic position is going to be very stable. And in fact, we're going to talk about specific reactions that deal with that allylic position just due to its stability. All right, so if we look here and we think about which of these are going to be the most stable, and we look here at, nope, sorry about that, as I accidentally closed it. Old man moment, my bad. Okay, so when we think about this free radical resonance, right, the more resonance delocalized the radical is, the more stable it is. So you can see here, we have this radical here on the outside, right, of our benzene ring. And if you notice, it can go through different resonance. So now that radical is moving throughout. So now I have essentially 5 resonance structures. So the stability of this free radical would be very stable. So the more pi bonds that are conjugated, the more stable that radical is going to be. And so if you think about this resonance stability, if I have a tertiary carbon, it's stable, right? Out of all the tertiary, secondary, and primary, tertiary is my most stable. But then if I think about this here, allylic, the allylic position, this is even more stable, right? Because of that extra resonance. So, you know, and then if I make it benzylic, right now I have even more stability here. This is going to be even more stable. So the more resonance I add, the more carbons I attach to my radical, the more stable it's going to be. And this is going to be necessary for when we think about the radical reactions, because you're going to start predicting what's going to react with the radical. Okay. All right, and so now this is an important thing. So vanillic is when the radical, okay, so allylic is when the radical is next to the double bond, like this. Vanillic is when the radical is on the double bond itself. So having a radical on the double bond itself is very, very unstable. It doesn't do well with radicals. So if you're ever thinking like, where's the radical going to form, on the double bond itself is probably the worst place to put it. If you have a regular carbon next to it, then that's going to be your best place. Okay. Any questions right there? All right. All right. So what is the geometry of alkyl radicals? Which of these is my geometry?
C. Try.
What was that?
It's C.
C. Yep. Trigonal planar, right? We can also think about it as very shallow trigonal pyramidal, but trigonal planar is the best one to think about that. So that's my preferred geometry. Okay. What is the general order of radical stability from most stable to least stable? So what is my correct order here?
C.
What letter?
C.
C. C is correct. So basically, yep. Remember, tertiary, then secondary, then primary, then methyl. So these have the same stability trends as carbocations, right? That's going to be important to remember. And a side note, I need to write a test tonight for my kids. Someone please remind me before we leave tonight that I need to write a test. Should I make it easy for them? I'm having a moment of old man weakness. Should I give them an easy test before spring break?
Make it hard.
You guys just have no love for my high school students. Just no love.
I was gonna say make it easy on them. I don't think they deserve to get like that much.
I'm gonna tell them I know 2 very angry Latinas, and they said they make you cry.
No. I didn't to make
the taller one was meaner than the shorter one. The tall one's especially mean. Okay. So which fishhook arrow sequence will generate the resonance structure shown below? So this is something I think you came in right at the tail end of, Melissa, is that when we draw our arrows like this, we have two, like our normal resonance pushing, right? But when we do radicals, you only have one, it's called the fishhook arrow because it's only got one side because it represents just one electron, as opposed to two when we do our normal arrow pushing. So which of these resonance structure, which of these arrows is going to give me this correct thing?
D.
So take your time, think about it.
Would it be D?
I don't know why my mic is not working. Is it working? Can you
It
hear
is
me?
now, yeah.
Oh, okay. I said
But
D.
earlier I was like really like faint.
I don't know
But
why. I don't know what's wrong with it.
Mm.
it works. It works now.
I need a new computer.
There you go. Find yourself a rich boyfriend or girlfriend, and then
No, my dad's gonna buy it for me.
or have a rich parent. There you go. That's even easier. As I hit pause. Yeah. So
I think it's a very strong intro.
I think it is too. I think health insurance is very undersold in this country, and the fact that I have really good health insurance. Okay. So you said letter D. So I will ask you this: how many electrons are moving from this picture to this picture? How many electrons are
3.
involved? 3, right? Because we have this radical, and then we have the 2 electrons present here. So how many arrows should you have in a free radical?
3.
3, right? And this is the only one that has 3 arrows. So whenever,
Doesn't
go ahead.
I'm just confused. I'm just confused about the third arrow because I thought that the radical like attacks the pi bond and then the pi bond attacks the radical, but then I don't know why there's a third one, if that makes sense.
I'm going to open up the whiteboard and then we'll do this, and this might make life a little bit easier. Hi, Gwen. We're talking about free radical arrows. So are you
And those are the ones that just push one
electron at a time?
Okay.
Yep. Are you back home, or are you just in a different location?
No, I'm just in my kitchen right now because my room is kind of a mess. So
That's fine. Okay. So when we think about our free radicals, right? So I'm going to draw this here. And so if we have an arrow pushing incident, and now this is the result of our arrow pushing incident, like this, right? The question becomes what's happening, okay? So what's happening, I'm going to label these carbons 1, 2, and 3. So Mag, what's the difference between carbon 1 and 2 in the before as opposed to the after?
One's allylic and the other one's, what's the other word? Phenolic?
Yeah.
Yes.
Essentially, you're forming a what there between 1 and 2?
You're forming a pi bond?
Yeah, you're forming a pi bond, right? So how many electrons do you need?
2.
Yes, so that's what's happening in reality, is that this is coming here like this, and one of these electrons is coming like that. They're coming together to form a bond, right? Now, how many bonds are left in my original double bond?
1.
1. So this has to go somewhere, so it goes to the outside like that.
Okay.
Does that make sense?
Yes. That makes
Okay.
sense.
So essentially your pi bonds are just splitting. That's what's called a homolytic cleavage, right? It's just one bond splitting upon itself. So the right side is being, so between 2 and 3 is a homolytic cleavage. Between 1 and 2, you're forming a pi bond. The Lord yoinketh and the as the Lord eateth. All right. So let's go and go back to our. Okay, so there's that one. Just as a quick note, Gwen, is that when we think about free radical stability, it follows the same trends as carbocations. So more resonance makes it more stable. Tertiary is more stable than secondary, more stable than primary, more stable than methyl. So if you remember the stability for carbocations, you know the stability for free radicals. Okay. Like ionic mechanisms, radical mechanisms follow patterns, but radical mechanisms are different. Radicals do not undergo rearrangement. That is one of the benefits of radicals, is that we don't have to worry about hydride shifts or methyl shifts or stuff like that. They just kind of stick where they're at. The only time you have to worry about that happening is if you have like a conjugated double bond nearby, right? Like if you have a resonance, that's the only time you have to worry about it. So like this carbocation here is gonna, it's a secondary next to a quaternary, so you have the methyl shift normally, but this here, not gonna happen. But the best thing is about our arrow pushing mechanism, and this is something that even I remember to this day, is that they essentially follow this general pattern of what's going to happen with your arrow pushing. So when you think about the arrow pushing, if you make just a flashcard that has these listed, they always follow the same pattern. So you're going to have something called the initiation step, and this is the homolytic cleavage. You're going to have, in addition to a pi bond, you could have a hydrogen abstraction. So essentially, you are just taking a hydrogen and an electron. So remember how we said like a proton is just the H with no electrons? A hydrogen abstraction is you're taking a hydrogen and one electron. So it's actually a hydrogen. Then we have halogen abstraction where you remove a halogen. All right, and so all of these steps are going to come into play when we do them. 5, we have an elimination. This is the reverse of an addition. So essentially, you're going to eliminate a radical, and then coupling. This is basically when your radicals come together. So you are going to see these 6 steps pop up in your mechanisms, and these are the only 6 steps that you can have occur in any type of radical reaction. And they all follow the same general pattern. So hopefully that'll help. Okay, so group the relationships among the 6 patterns, and you see that there are only 3 processes, forward and backward. So a homolytic cleavage is where you break a single bond and you form 2 radicals. But when 2 radicals come together, that's a coupling, right? We can have a radical addition to a pi bond, or that radical can form a pi bond and kick off my leaving group, and that's an elimination. We can have a hydrogen abstraction, or we could have, this should be halogen abstraction. So, but that's all right. So this should say halogen abstraction going backwards there. All right. Okay, so next up, it says the steps in radical mechanisms are classified as either initiation, termination, or propagation. So essentially, every radical reaction that you can think of will always have one initiation step. That is when you form your radicals at the beginning of the problem. Every radical mechanism is going to have a termination step. That's when your radicals stop. They, come back together and you have no more radicals. Propagation, you'll always have at least one. You usually have multiple propagation steps, right? So you always have a start, you always have a finish. It's the amount of middle steps that is going to change. Does that make sense? So initiation, always one. Termination, you always have one. And in the middle, propagation, you're going to have some amount. So in our initiation step, this is where a free radical species forms from some type of whatever. Our bond is essentially going to split like this, and we are going to form 2 radical species. All right, so normally when we do our mechanisms, we're going to use just one of them at a time. Propagation is any step. So the way to think about it is, this is the way that I kept it straight in my mind, is initiation, think before no radicals, after there are radicals. So before the step, there are no radicals. After the step, there are radicals. That's initiation. Propagation, the way that I like to think about it is before the step, there are radicals. After the step, there still are radicals. They're just moving about, right? Like I can do an addition to a pi bond, radical still here. I can do a hydrogen abstraction, radical still here. I can do a halogen abstraction, radical still there. I can do an elimination, the radical still there. So in propagation steps, there's a radical before and after. It's just being shifted about. All right, and then coming down to here. Termination. This is when 2 radical species react to form non-reactive species. So this is when you have a radical before the step and no radicals after. And that's how I remember that. It's propagation, none before, you have them after. Sorry, that's initiation. Propagation is before and after, and termination before but not after. So this just helps you keep straight what's happening. And so essentially what's going on here is just the order in which your radicals are reacting. So blank and blank can be used to form radicals. Which letter is correct?
It's A, right?
Yes, light and high temperature. So when we see one of 2 arrows, there's going to be 2 things that are going to be, well, I guess it depends on you write them. You could write light, you could write H nu, right? Or this is Planck's constant times frequency, right? Which is the energy of light. I know you guys remember that because I taught it to you, and I know it's still in your head. The lie he tells himself. So that's both are representative of light. You can either write light or you can write that. And then you have the delta sign for heat. Sometimes you might even see like this little arrow kind of thing like that, where it looks like a wavy arrow coming down. That can also represent light. So any one of those is a good representation, and it just depends on the professor on how they like to do that. So some professors like to keep it clean, some professors like to keep it traditional. Just depends. All right. Okay, so let's talk about the chlorination of methane. So whenever you have a alkane of some sort, say like you have CH4, or you have methane or ethane or whatever, what's the only reaction mechanism that you can do to do something to an alkane? Do you guys know?
Halogen?
Not just any halogen, radical.
Oh,
So if you have an alkane that only has carbons and hydrogens, no pi bonds, no nothing, just regular alkane, radical halogenations are the only steps that you can do. That's the only reaction that's going to react with your methanes and ethanes and other stuff. The only other thing that is strong enough to react with those are bases like terpetal lithium that basically ignite when they come in contact with air. So this is a general thought here, is that don't, and just know that this is going to come up at towards the end or at the start of the next semester when you do synthesis, is that you have to know what reacts with what. All right. But going now into this, in our initiation step, whatever it is, whatever forms are radicals, see we have HV, HNU, right? So we see here that Dr. Dewis is a traditionalist. I like it. So this is just our light, right? And so what happens is that we have homolytic cleavage. We just break it, and now we have two radical species. And here's the important thing. You're going to use one for the first part, and you're going to store the second one away. It's going to just hang back. You're only going to use one at a time, all right? But just know that you have a second one there, okay? So now going into here into our next step, we have two propagation steps. So we have methane, and we have our halogen radical. We're going to do a hydrogen abstraction. So this bond is going to have a homolytic cleavage. One of the electrons and the hydrogen are going to form an HCl, right? The other hydrogen or the other electron in that bond is going to form a radical right here, okay? So we had a radical before, now the radical is there. This is a propagation step, all right? We went from a halogen radical to a carbon radical, all right? Now, the next one is something called a halogen abstraction. Our carbon radical is going to attack another equivalent of Cl2 like this, right? So it's going to take one of the chlorines along with an electron and form the bond here. And then this one is going to form this chlorine radical there. Okay. So does anyone have a guess as to what step is next? We had an initiation, we had two propagations.
termination.
Yep. So we have, how many radicals do we have? How many radical species do we have floating around in our solution right now? We have this one we just formed, but what did I tell you to do earlier? Remember we had that second one that's still kind of just chilling out, right? So this is important to remember, that when you do this, you always have this one that's just chilling out to the end. So now when I come here and I look down at my next step, we have our termination, right? We could have a coupling like this, right, where the two chlorines come together, the two chlorine radicals that I have. I could have this type of coupling or this type of coupling, right? So basically, when you do radical reactions, you get all sorts of weird products because radicals are just very, very reactive. But this is probably the one that's going to make the most sense for you, is that chlorine that we produce in the first step that was chilling out, and then the chlorine that we produce in the third step are going to come together, right, and form our dealie. Does that make sense? Okay.
Just to double check the chlorine from the first step came like the okay. Oh, no, wait, actually, never mind. I just figured it out.
Yeah. All that matters. Hello, Matthew. And I want to say congrats to all of you. You guys all did better on the last test. So that's great news. All of you improved, and I'm very happy for all of you. I know not all of you are where you want to be, but the only thing you can do is just keep working forward, right? So this is working, right? Your test scores are improving. So that shows that this extra section is working. So hopefully it'll, I'm not saying hopefully, I know it will. If you guys keep doing what you're doing, by the time you get to your final, you'll all do well. All right, so chlorination of methane. The sum of the propagation steps gives us the net reaction. So essentially, when we go through the whole thing, CH4 plus Cl2 will give us CH3Cl plus HCl, right? Propagation is a chain reaction. The products for later step surface reactants, right? So chain reactions in chemistry generally are reactions that kind of just keep forming products and they go about their business until they are neutralized, but that's it. So this is what the overall reaction scheme looks like for this. But Gwen, in reality, how many Cl2s did we use in this reaction mechanism?
2.
We used 2, right? We used one in the first step, and then we used the second one in the halogen abstracts in the second propagation step, right? So even though we use 2 chlorines, the way that we keep our things all settled, this is the net reactant, right? So this is it. Okay. So now when I look here at our chlorination of methane, polychlorination is difficult to prevent. So like if I said, Gwen, here's all the stuff you need to go make me a methyl chloride, and I said, go produce just this, you probably can't do it, because once this first reaction happens, this is more reactive than this. And then this is more reactive than this. And so what's going to happen is, in reality, you are going to make a lot more of these products than you are of just the methyl chloride. So just trying to put one chlorine on is very difficult. The only way that we can get around it as organic chemists is that we would use like a 20-to-1 ratio. So I would put 20 equivalents of methane to 1 equivalent of chlorine just to prevent that from happening. But this is just the idea here. I think it's 20-to-1. I forget what that ratio is. It's a high number. But basically, this is just so that we can get the monochlorination product. But this is something to worry about. Because this is a general question that professors like to ask is, what's one of the problems of a radical mechanism? And Melissa, what would you say now that I told you? What's one of the problems of a halogen radical mechanism?
Every other product is more reactive than the last one, so you'll always have more product than like what you're looking for.
Yep. You're not going to get your mono substituted product alone. You're going to get the other ones too. Exactly right. Okay. So the next thing to think about is, what are our radical initiators? Meaning, when I think about this type of reaction, what's actually going to be a possible radical? So the 3 that we have here are dihalides, so anything like Cl2, Br2, or whatever. Alkyl peroxides, things like hydrogen peroxide, you basically break that OO bond. And then acyl peroxides. So these are your 3 common initiators that you'll see as you go through reactions. Meaning, like if you see ethane plus, Cl2 and heat or light. So what do you think this over the arrows is do you think this is a good indicator? If you see heat or light over the arrow, you should immediately think radical reaction, because remember, those are the 2 things that initiate radicals, right? Also knowing that if you have a dihalide, an alkyl peroxide, or an acyl peroxide in the reaction, that's going to be your dead giveaway that it's a radical reaction, all right? Okay, now we have something called radical inhibitors. Radical inhibitors are something that prevent radical reactions from continuing on in their chain. So radical, basically, they prevent chain processes. So you limit propagation steps. And so you can use hydroquinone or oxygen. These are very good at slowing down radical mechanisms. So Gwen, I think you're a vegetarian, right? Or was that?
I used to be.
Okay.
Oh, yeah. I think Maggie is though.
Man, you're right. You're okay. You're
Yeah.
vegetarian. So if you have a high vegetarian diet and you eat a lot of colorful fruits and veggies and you drink a lot of water, do you know what one of the best side effects of that is? Your skin
Um,
usually looks fantastic. Do you know why?
not sure, but I mean, I've heard that like water helps with like clear skin, but I'm not sure why.
This is it right here. So one, water is good for you because it helps clean out your system, right? It keeps everything moving about and whatnot. The more water you have, it keeps all of your ions in balance and everything else that you need to live and everything else. Second, being in the sun produces radicals. Sunlight mutates your DNA. We have ways to fix it, so don't worry. It's not like you're going to be permanent. But this is why people get sun damage. You are all in Arizona. How many of you have older Caucasian friends that look like they're leather handbags? You know what I'm talking about. Don't act like that's not a thing. It's because skin gets damaged by sunlight. Also, breathing in air like pollution and stuff damages your skin. Think of all the colorful fruits and veggies and all that stuff, things like chlorophyll, all the different dyes that give fruits and veggies. They all have huge conjugated systems. And so what happens is those dyes in your fruits and veggies can readily pick up and remove free radicals from your body. They limit the amount of damage you do. And when you drink enough water, they basically flush them out in your urine, right? Because then they can be flushed out pretty easily. So this is why the more fruits and veggies you eat, the more colorful fruits and veggies you eat, the better it is for your health overall because you start removing that. So this is a very important reason why you should eat all the fruits and veggies you can, particularly those that have rich like purple and orange colors and stuff like that. They're good for you. So um, just a side note there, but this is one of the many things because these types of inhibitors are what is going to remove these, or they limit the rate that radical reactions go through. Because remember, radical reactions, radicals themselves are extremely reactive and will keep reacting and they'll keep destroying things. They don't stop until they run into something like an inhibitor. So when we think about how inhibitors work now, just looking on the right side of this slide, is that you can see that when my radical comes in, it takes this hydrogen from hydroquinone, right? Does a hydrogen abstraction. Now this has this radical. Now this is stabilized by what? Resonance, right? So it's a little less reactive because now it has resonance stabilization. But also on the other side, if this undergoes another hydrogen abstraction and now I have two radicals, this can have a mechanism that will give me benzoquinone. So my hydroquinone can react with two radicals and now it makes a stable intermediate. It's no longer reactive. The radicals have been eliminated. All right, so this is what these types of things do. They essentially make more stable intermediates that don't have the free radicals floating about. Does that make sense? Okay, you guys look a little confused, but just know that if I was to ask you, Gwen, what would you tell me how radical inhibitors work?
I would say that they prevent like reactant radicals from continuing to do damage to certain or keep reacting basically.
Yep, they prevent radical propagation.
Okay.
That's the fancy term. And then they form stable products like hydroquinone to benzoquinone. They make stable products that don't have any reactive radicals on them. So that's the benefit of radical inhibitors. I should eat more fruits and veggies. I haven't had any today. Although on the pizza I ordered, I did get mushrooms. I don't know if that counts or not. Don't judge
I
me.
have some recipes that are really good if you
Oh.
want them.
Maybe I should take them from you. I see. I help you out. You help me live a few extra years in the retirement home. I'm not kidding. I just got my new shoes. You know what kind of shoes I got? Proof that I am an old man.
Are they New Balances?
Oh, they sure are. Buddy, are they comfortable?
Oh.
I just realized that one day I went from Nike to New Balance, and I didn't know when that transition happened.
Well, I feel like you're still in because I feel like New Balances are kind of trendy still. Like people wear them.
I know, but then I got some slacks online. So I think that I undid any good I did. That's okay. All right. So let's go ahead and continue on here. So questions, because I know you guys love questions. Identify each of the mechanistic steps below. So go ahead and try and identify those. I'm gonna go grab a drink. I'll let you guys work on this. I'll be back in like a minute. Okay, so which one did you guys come? What is step A?
Initiation.
Yep, no radicals before, radicals after initiation. What is step B?
Propagation.
Yep, radical before, radical after. What type of propagation step is it? What is it taking?
It's taking
A hydrogen?
Mm-hmm. Hydrogen abstraction. What about the next one?
it's also propagation.
Mm-hmm. What kind of propagation?
Isn't it the halogenation thing?
Halogen
when you-
abstraction.
Yeah.
And then finally D.
Termination.
Mm-hmm. It is a coupling step, but yes, that is a termination. All right. So this right here are the 4 steps you always have for a radical halogenation. 1 initiation, hydrogen abstraction, halogen abstraction, termination. I apologize, I'm eating my slice of pizza. All right, which of the bonds would be the most susceptible to radical formation?
Oxygen, oxygen, single bond.
Yep. Or oxygen single bond. Remember that is one of our types of radicals we can form, right? When we think about our peroxides. So like HOOH or ROOR. So halogens bonded to halogens, oxygen single bonded to oxygen. Those are going to be extremely susceptible to radical formation. Good job. Questions? All right. One more question here. This one says, what is the primary use of the following compounds in radical chemistry?
Wouldn't the first one be an initiator since it has the oxygen single
Mhm.
bond with oxygen? Okay.
Yep. Anytime you see an oxygen single bonded, you're right. Immediately think initiator.
I know the second one would be an inhibitor.
Mm-hmm. The second one's inhibitor, right? That was our quinone, the hydroxyquinone. So if you see a benzene ring with 2 OHs coming off of it, so the correct answer is D. All right, halogenation thermodynamics. So what do you guys remember about thermodynamics?
entropy. And enthalpy.
Good enough. So delta G is our Gibbs free energy of our product. So if delta G is negative, is our product favored? Yes or no?
No, because wouldn't it be non-spontaneous?
It's spontaneous if it's negative.
Oh, so then it is product favored.
Yep. So basically, we have to consider two terms, right? We have enthalpy and entropy. So entropy, if you remember, is degrees of freedom, how many orientations we have, right? So entropy comes into play if I have if I go from a solid to a liquid or liquid to a gas, entropy increases, right? So if I increase entropy, if entropy is positive, that will help my reaction be favorable. But with halogenation reactions, we start with two molecules, we end with two molecules, and they're usually in the same phase. So we typically ignore the entropy part of our reaction, right? So we can say entropy is not a consideration. That makes our life a lot easier here, thankfully. Well, it makes your life easier. I don't have to do this. Basically, now we just have to take a look at the enthalpy, which is bonds broken versus bonds formed, right? So if you remember our equation, right, when we think about this, do you remember what our delta H formula is for bonds broken and bonds formed?
Isn't it
Formed.
product? You can go, Matthew.
I think it's bonds formed minus bonds broken.
Okay. So when we look here, right, we have our bond dissociation energy. So you're going to have whatever type of hydrogen carbon you are breaking, right? And then whatever type of halogen bond, right? So then you